average of a sigma e to the minus beta h, and then you have sigma k plus 2 divided by z, by the partition function, right?
Right.
Correct? So now,
Yes.
this I can write it as sum over sigma e to the minus beta h, sigma k, then sigma k plus 1 squared, sigma k plus 2 divided by z, right?
How you do that?
Well, because sigma is equal to plus or minus 1, and therefore sigma k plus 1 squared is always equal to 1, right?
Oh,
In other
yes.
words,
This is for Potts model, right? So,
for easy model, this is for easy model, not Potts. This is equal to 1, because sigma k is equal to plus or minus 1. For Potts model, you cannot do this, because sigma is equal to a number between 1 and q.
so
It's not
it's
true
just a mathematical manipulation using the fact that Ising model
yeah,
has plus and
yeah,
minus.
but I know that you like mathematical manipulations, so so it's just related to the easy model. And now you see that this is equal to sum over sigma e to the minus beta h sigma k plus 1 times sigma k plus 1 sigma k plus 2 divided by z, right?
Right.
So, and now this is, and now I take the derivatives, I do what I wanted to do, and so you see, that's how it works. Is it okay now?
Yes, yes.
Good, excellent. Any other questions? Question from you guys? So let me see who's there. 1, 2, 3, 4, 5, 6, and 7, and 1 is missing because it has a medical, whatever. All right, so we can go on then. Sorry. Let's move on. So today's lecture is about something called transfer matrix. Have you ever heard of the transfer matrix?
In quantum mechanics, potential barrier.
No, that is the transmission matrix, is a different thing. That is the scattering matrix, right?
But they call it transfer, so.
Okay, well, they call it the way they want, but it's not the transfer matrix. All right. So you've never heard of this in statistical mechanics, right?
Right.
Okay, so, well, the transfer matrix is the most general tool that we have at our disposal to compute the partition function of models in statistical mechanics defined on a lattice, okay? Not continuous models, not models like interacting gas of particles, but models defined on a lattice like the Potts model, the easy model, and things of this type. So let me first explain why it is needed to find a general tool in order to compute the partition function. And let me explain it with a model that we already solved, the easy model, right? So we know that if there is no magnetic field H, then the easy model in one dimension is exactly solvable by the recursion method. Unfortunately, if you try to apply the recursion method with a magnetic field, things are not working anymore, right? Why? Because let's see, suppose that we try to apply the recursion method as we have done before. So we'll have e to the beta j sigma 1 sigma 2 plus h sigma 1, and then whatever, and then we sum explicitly over the last spin. E to the beta j sigma n minus 1 sigma n plus beta h sigma n. So now we perform the summation explicitly over sigma n. So what do we get? We
Sorry, Professor.
Yes.
Is it plus or minus h sigma? Because
It's minus.
yes.
Right. It's minus. The way I wrote it is minus. Thank you. All right. So let's now perform the summation over sigma explicitly. So this summation here.
Professor.
N. Yes.
I think the summation in the middle is somehow weird because the summation is over sigma n minus 1, but the term is sigma 1 and sigma 2.
Yeah, of course. I mean, here there are all the other terms. I mean, all these dots here means that here you have e to the beta j sigma 2 sigma 3 minus h sigma 2, and then e to the beta. You see, all these dots are all the exponentials. Beta j sigma 3 sigma 4.
Oh, okay, I get it. Thank you.
You see what I mean? Of course, I'm not forgetting those terms, but I'm saying let's sum explicitly over the last one. So if I sum explicitly over sigma n, you see what happens. I have 2 cosine hyperbolic of beta j sigma n minus 1 minus beta h. And now you see something interesting, that in the case in which I have a magnetic field, H, then this cosine hyperbolic is not anymore independent on the value of sigma n. It depends on sigma n explicitly. And therefore, with a magnetic field, I cannot anymore write Zn equal to something times Zn minus 1. This is not true anymore. Why? Because the variable sigma n, after performing the summation over sigma n minus 1, the variable sigma, after performing the summation over sigma n, the variable sigma n minus 1 remains in this expression, and therefore now when I perform the summation over sigma n minus 1, I will have to take it into account, right? This cosine hyperbolic. And everything becomes extremely complicated. So the recursion method cannot be a general method to solve problems in statistical mechanics. Unfortunately, what can we do? This is life. Okay? So therefore, let us try to cook up a different method. So, and again, I will use my easy model as a, let me put a minus sign here just to be uniform in the notations. I will use my easy model as the toy model. And my method is going to be called the transfer matrix method, so, which starts here. So, what is the point?
Sorry.
Yes.
I mean, you put the minus sign, and what about the Hamiltonian, the first Hamiltonian with the plus sign? is it like actually a plus or minus sign? Or
It doesn't matter, right? I mean, it's a matter of convention.
yes. Okay.
Okay. I mean, you know, up to here, it's with a plus sign. Then from here on, it's with a minus sign. But it doesn't matter. It's a convention, right? I mean, you know, age is a variable, can be positive or negative. I didn't specify what it is. So it's the sign that I put in front of it is completely arbitrary. All right, so I take this model. Now, it's true that up to now, in order to use the transfer matrix method, we have been using this model with open boundary conditions. Now, for transfer matrices, it's much better to use periodic boundary conditions. Periodic.
Sorry.
Yes.
Can you specify what's the difference between open periodic condition and
Well, so open boundary conditions means that I have a chain in which my spins are put like this, right? I mean, and the first and the last spin are interacting only with this guy and the last one with this guy. But they are different, the first and the last, because every single spin in the bulk is interacting with two spins, and the first and the last are interacting only with one. Okay? Periodic boundary conditions means that I put these spins on a ring. Like this. And therefore, each one of these guys is always interacting with two other guys. Right?
Yes.
If I put them on a ring. Now, how do I specify that I'm using periodic boundary conditions? I say sigma n plus 1 is equal to sigma 1. Okay? Now, should it matter which boundary conditions I use? Yes or no? Does it matter?
Yes.
Yes?
Of
Well,
course.
it depends. Yeah, of course, in general, it matters. So
if not, you will not mention it.
Is there a limit in which it doesn't matter what boundary conditions I choose? I always get the same result. Did you get the question?
Yes.
I think I don't get it well.
So is there a limit, a physical limit for a system in statistical mechanics for which it doesn't really matter for the partition function, for example, or for the free energy vector, which boundary conditions I use? I always get the same result, no matter what boundary conditions I select. What is the limit in which I always get the same result?
If you take the n very large?
If I take the thermodynamic limit. Okay? That's correct. If I take the limit of n very large, so the number of spins, the total number of spins goes to infinity, I mean the thermodynamic limit, it doesn't really matter whether the first and the last spin are free to fluctuate or they are bound together in a ring, which boundary conditions I choose. Because at the end of the day, most of the properties, actually the entire free energy is determined by the bulk. And boundary conditions will give me a contribution that is, proportional to the boundary, but that doesn't scale like the volume. So it's irrelevant in the thermodynamic limit. That is, by the way, why, I don't know if you ever took a course in solid state physics. Did you ever take a course in solid state physics?
Yes.
We are taking it now.
Right. So, You know that when you compute a lattice, when you compute bands in solid state physics, you always take periodic boundary conditions and you quantize your momenta, right? In power proportional to 2 pi over L, where L is the linear size of your system, right?
Yes.
Yeah.
So why can you take periodic boundary conditions? Have you ever seen a metal that is wrapped up in a torus? I mean, if you have a 2-dimensional system, taking periodic boundary conditions, meaning that I identify this guy with this guy, and I identify this guy with this guy, this is what it means to take periodic boundary conditions, means in practice that instead of considering this square, okay, I'm considering a torus. So the torus is practically the only thing that I'm able to draw. Is this, is a donut, right? Instead of considering, actually I can even draw it better than this. Look at this, what a fantastic torus, right? When you take periodic boundary conditions into them in a 2-dimensional system, in practice, you go from a square to a torus. Have you ever seen a metal wrapped up looking like a torus? I mean, when you compute the properties of the band properties of iron, is it a 3-dimensional torus? It's not, right? But it doesn't matter because in any case, you're interested in the properties in the bulk in the limit, in the macroscopic limit. And therefore, it doesn't matter which boundary conditions you select, whether you select open or periodic boundary conditions. You always have this freedom as a theoretician to perform the calculation the way you want, as long as you're interested in properties in the thermodynamic limit. Okay?
Professor.
Yes.
I'm afraid I don't quite get your point. Why is it in 2D you can calculate the square to become torus? And
Well,
I mean,
so
what's the connection with thermodynamics?
no, look at this. If I identify these two boundaries, what happens? That I go for, so let's wrap it up. You go from here to a cylinder, right? If you identify the 2 green boundaries, what happens? That you go from a square to a cylinder. Right?
Sorry, are you assuming that it's a circle?
No, I'm saying identify this boundary A, this one, identify this boundary with this boundary. Say every point here is equal to a point there. What does it mean geometrically? It means that I'm taking this piece of paper and I'm wrapping it up in a cylinder. You see, I'm gluing this boundary with this boundary, which means that I take the piece of paper, I wrap it up, and I make a cylinder, right?
Oh,
This is,
I get it. And is
You
it
got
also
it?
the same with the other boundary? So you can
and
make a
then
torus
now
with-
you do it with the other boundary. You identify this guy with this guy, right? So you wrap it up and you go from a cylinder
to
to a
torus
donut, to the
or
torus.
donut. Oh,
You
okay.
see?
Okay,
So
thank
this
you.
is what it means to take periodic boundary conditions for a 2-dimensional system. In 3 dimensions is more complicated, but so it's hard to visualize, but technically this is what it means, okay? So what I was trying to say is in life, in real life, you never compute the properties of an easy model of on a torus because your magnetic material even if it's two-dimensional, is typically you know, a square or whatever. Is not sitting on the surface of a torus, right? Same thing when you compute the band structure of a, let's say, two-dimensional metal or three-dimensional metal, is not sitting on a strange toroidal geometry. Is a square or a cube or whatever, right? A simple system. And then you can ask yourself, why I can use these strange, mathematically strange periodic boundary conditions to compute the properties of a system that does not have periodic boundary conditions? And the answer is because I'm interested in properties in the thermodynamic limit. If I'm interested in things in the thermodynamic limit, then in practice, this means that I'm taking the limit of n going to infinity, and what happens at the boundaries is irrelevant. So I can choose the boundary conditions that I prefer. Okay, is it clear now?
I think I get a picture, but I'll think again.
Okay, good. Anyway. All right, so now let us now consider again the easy model with periodic boundary conditions, and let us try to compute the transfer matrix. Sorry, to compute the partition function. So the partition function then is going to be equal to sum over sigma 1 equal to plus and minus 1 to sum over sigma n equal to plus and minus 1. And then you're going to have e to the beta j sigma 1 sigma 2 e to the beta j sigma 2 sigma 3, etc., all the way to beta j sigma n sigma 1, right? Because sigma n is interacting with sigma n plus 1, which is equal to sigma 1 by definition of periodic boundary conditions. And then you will have times all of this times e to the beta h sigma 1, e to the beta h sigma 2, etc., e to the beta h sigma n. So now we want to compute this sum. Let's write it in a more symmetrical form. And the more symmetrical form is the following: sum over sigma 1 equal to plus or minus 1, sum over sigma n equal to plus or minus 1 of what? Of e to the beta j sigma 1 sigma 2. Now here I have sigma 1 and sigma 2. I also have two terms here in which appear sigma 1 and sigma 2. So let's take half of this and half of that and place it here. So beta h over 2 sigma 1 plus sigma 2. Why I put half? Well, you understand it in a second, because if you write up the next, is going to be e to the beta j sigma 2 sigma 3 plus beta h over 2 sigma 3 plus, sorry, sigma 2 plus sigma 3. You see, I put half of the term with sigma 2 here in this first exponential, and the other half I put it in the second one. This way I obtain the most symmetrical way of writing this sum. Symmetrical in the sense that each individual exponential is symmetrical by exchange of the two indices 1 and 2, 2 and 3, and whatever. And so on and so far. You go on and you do this all the way to the end. So the last term is going to be e to the beta j sigma n sigma 1 plus beta h over 2 sigma n plus sigma 1. Okay? All right, so you agree?
So the
Yes.
Sorry? So the,
sigma 1 in the last term coincides with the sigma 1 in the first term.
yeah, so you see half of the sigma 1 is sitting here, half of the sigma 1 is sitting there. So overall, if you count, so I'm essentially, I have the same, what I wrote here is equivalent to what I wrote above. Okay?
Yes.
I just have to interrupt at 2 minutes. So I will be back in 2 minutes. I apologize.
Maha? Maha?
Yes.
Yeah, okay, I want, why did he say he chooses to write halves of beta and sigma 1?
Did he say what?
Why did he choose to write the halves of beta and sigma 1?
Okay, here I am.
You
Is
can
there a
ask him.
question?
I think he's back.
Is there a question?
Yeah, I think it's from Pelus.
Yes. What is the question?
Okay, yes, I wanted to find out why you chose to write the halves of beta and sigma 1.
Why I wrote it in this way?
Yes.
Oh, you will see now why. Wait a second and you will see. So let me define now V of sigma prime equal to exponential of beta j sigma prime plus beta h over 2 sigma plus sigma prime, right? So you see that if I use this definition, well, you see that this object here is, for example, V of sigma 1, sigma 2. This one is V of sigma 2, sigma 3, and so on and so far, right? You agree? Yes. So in practice, I rewrite then my partition function Z as the sum over sigma 1 equal to plus and minus 1, sum over sigma n equal to plus and minus 1 of V sigma 1, sigma 2, V sigma 2, sigma 3, V sigma n, sigma 1, right?
Yes.
Okay, so now each one of these guys, sigma 1 and sigma 2, can be equal to plus or minus 1, right? So each one of these guys here can be seen, can be interpreted as a matrix, right? This guy here can be seen as a matrix that has two indices is a 2 by 2 matrix, and the entries e to the beta j plus beta h, e to the minus beta j, e to the minus beta j, e to the beta j minus beta h, where here I have my indices +1, +1, -1, and -1. You see? Each V can be seen as the components of a 2 by 2 matrix. You agree?
Yes.
Is it because of the summation?
Well, I can see it as a matrix always, right? And the reason I can see it as a matrix is that my variables have discrete values. So my local phase space on each lattice site is discrete, is a discrete set. And therefore I can see this object here as a matrix. Now, the fact that I have a summation, as you mentioned, means that I can interpret now this as being equal to the trace of V to the power n, of the matrix V to the power n. You see this? Why the trace? Because let's look at this product here. Among these sums, I have also the sum over sigma 2. So if I put it here, sum over sigma 2 equal to plus and minus 1, you see that this gives me V squared. The product of the two matrices, by definition, is the product of the components in this way. So this is V squared. Now, therefore, all these guys, since I'm always summing over the indices that stay in between, these two, etc., this is the product of n matrices, is V to the power n. But now I have the, sorry?
It's the same matrix, right? Because
yeah, it's always the same matrix. Yes, it's always the same matrix. So therefore, this is V to the power n. And now why the trace? Because you see that I'm summing over sigma 1 explicitly. And if I have a matrix and I take the two indices of the matrix elements equal and I sum over them, this is by definition the trace. Okay?
Because the only thing that's left is the sigma 1 in the first and the sigma 1 in the last. So
yes, exactly. So these are the only things that I did not sum over, but now I'm taking them equal and I'm summing over sigma 1, and therefore I have a trace. Okay? So what I just discovered, therefore, is that with periodic boundary conditions, the partition function is equal to the trace of this 2 by 2 matrix V to the power n. By the way, the matrix V is called the transfer matrix. Okay? Yes.
The point that when you said sigma just sigma 1 and sigma 1 remains, I didn't get the point.
Well, so you see that, so this thing here can be written as the sum over sigma 1 equal to plus and minus 1 of the sum over sigma 2 V sigma 1 sigma 2 V sigma 2 sigma 3. Then to do it better. So of let me do it here. So I will have the sum over sigma 2, V sigma 1, sigma 2, V sigma 2, sigma 3. Then I sum over sigma 3, and then V sigma 3, sigma 4. And then I sum over sigma 4, V sigma 4, sigma 5, etc., 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 all the way to V sigma n sigma 1. So the last summation is going to be over sigma n. So all these summations will give me the product of the matrix V. You see that sum over sigma 2, V sigma 1, sigma 2, V sigma 2, sigma 3 is equal to the matrix V squared, matrix element sigma 1, sigma 3. This summation is by definition the matrix element sigma 1, sigma 3 of V squared. Therefore, all these summations will give me the matrix element of V to the power n with which indices? Well, here I have a 1 and a 1, so sigma 1, sigma 1. And then the last summation that remains is sum over sigma 1. I didn't do this summation. But sum over sigma 1 of V to the power n sigma 1, sigma 1 is equal to the trace of V to the power n. And therefore, I get this identity that Z is equal to the trace of V to the power n. Okay? Did you get it?
Yes.
Good. Excellent. So I can
Actually,
erase. Yes.
why you can put out sigma 1 outside? I mean, yeah, you have sigma 2, right? And what can the sum be? I mean, you can commute the sum or something.
But I can also perform the summation over everybody but sigma 2. But you see what happens if, so in order to do that, I will just take this guy, put it in front, and then leave, actually, no, I will do the opposite. I will do the following. I take this guy, put it at the end, and then start summing over sigma 3, sigma 4, etc. I sum explicitly over sigma 1, but then I will have at the end left behind sigma 2. So what I will have is sum over sigma 2, V to the n, sigma 2, sigma 2. It doesn't matter which one I sum. At the end, I will always get a trace of V to the power n. It doesn't matter in which order I sum them. You see what I mean?
Yes. But my
Okay.
question is, when does the order of summation matters?
Not when you have periodic boundary conditions. When you have open boundary conditions, it does matter. But when you have periodic boundary conditions, it doesn't matter. But when you have open boundary conditions, actually, you don't get this identity. You don't get this is equal to the trace. What you get is that the partition function is actually equal to Z is equal to V to the n, and then you have the matrix element of this on over 2 states that represent the boundary conditions. But let's leave it aside. I mean, it's not important. So when you have periodic boundary conditions, it doesn't matter in which order you perform the summation. You can leave behind sigma 2 and sum over all the others. You can leave behind sigma 3 and sum over all the others. It doesn't matter. You will always get trace of V to the power n, no matter what you do. Okay? And now,
Yes.
okay. So now, why is it interesting to write it this way? Well, first of all, the matrix V sigma sigma prime is a symmetric matrix, right? And being a symmetric matrix, it has real eigenvalues. Okay. Therefore, we can think of diagonalizing it. So performing a rotation on the matrix V that will put it in diagonal form that for this particular case is going to give us two eigenvalues, lambda plus and lambda minus. And let's say that lambda plus is greater in absolute value than lambda minus. Lambda plus absolute value is greater than lambda minus. All right, so now, since Z is equal to the trace of V to the power N, you see that I can now write this as trace of V U minus 1, V U minus 1, V, etc., U minus 1, V. Sorry. Yes. Why? Because, so these are N V's, and then in between each one of them, I put a resolution of the identity. This is equal to the identity. By definition, is U times U minus 1. Now, I can also put a resolution of the identity in front of everything. So U minus 1, V, U minus 1, etc., U minus 1, V. And now I can use the invariance property of the trace, right? So you know that if the trace is invariant under cyclical permutations, which means essentially that I can take the first guy and put it at the end. I can take this first guy, put it at the end, and nothing is going to change, right? So, which means in practice that this is equal to the trace of U minus 1, V.
Sorry.
Yes?
How did you get the second line?
Well, the second line, I just introduced another resolution of the identity here in front.
Okay.
And then U minus 1, V, U. So now using the cyclical property of the trace to reshuffle this new resolution of the identity, you see that what I get is D, the diagonal matrix times the diagonal matrix times the diagonal matrix n times. In other words, well, I'm not telling you anything spectacular. The trace of V to the n is equal to the trace of the diagonalized matrix to the power n. But the trace of D to the n is very simple to write, is lambda plus to the power n plus lambda minus to the power n. That's it.
Oh, sorry.
Yes?
Did you move the first matrix to the last term?
Yes. I
Oh,
use this.
because the trace property.
Yes, because the trace is invariant under cyclical permutations. Right? So now you discover something quite interesting. You discover that the partition function, once I write it down in terms of this transfer matrix, is just the sum of the nth power of the eigenvalues. Okay?
Yes.
All right, so now let's take our problem. The problem was, so this matrix, and let's diagonalize this matrix. I have to solve this equation. And what I find in general is that lambda plus and minus, if you solve this problem, I invite you to do the calculation, is E beta j cosine hyperbolic beta h plus and minus, and then you will have the square root of e to the beta 2 beta j cosine hyperbolic beta h squared minus 2 sine hyperbolic beta j. Okay? Perfect. Now, lambda plus is in absolute value greater than lambda minus. In particular, what you have is that when h is equal to 0, lambda plus and minus is equal to, if you do quickly the calculation, e to the beta j plus and minus e to the minus beta j. So this is what comes out. Great. So now that we have this, let us compute the partition function z, and what we get is 2 to the n times cosine hyperbolic of beta j to the power n plus 2 to the n sine hyperbolic beta j to the power n. So this is the partition function
Professor,
of the, yes?
the second last line, did you just set H0? I do not get the line.
Yeah, so, well, if h is equal to 0, then this follows.
Okay.
If you set above h equal to 0, then you will see that this is true. All right, so this is the partition function that we get. And now comes a question. We already computed this partition function, right? And what we obtained, do you remember, by recursion was 2 to the n cosine hyperbolic beta j to the power n minus 1. And, well, this is not the same as the one that is written above. Why is not the same?
Sorry. This partition function is for h equal to 0, right?
Yeah, it's for h equal to 0. Yes, absolutely.
And what's the question for not being the same?
Well, the one I calculated by recursion is not the same as the one I calculated with the transfer matrix. Why? I use two methods. I compute the partition function in these two methods, but I don't get the same result. Why?
We didn't use the same boundary conditions.
Exactly, because we have different boundary conditions. So in general, the results are different, have to be different, right? However, they should be the same in the limit in which limit?
N goes to infinity.
N goes to infinity. So how do we see that? Well, we see it in a very simple way. If n goes to infinity, z is lambda plus to the power n plus lambda minus to the power n. I can write it as lambda plus to the power n times 1 plus lambda minus over lambda plus to the power n, right? And in the limit for n going to infinity, since lambda plus over lambda, lambda minus over lambda plus in absolute value is smaller than 1, this will tend to lambda plus to the power n. I mean, we'll go like lambda plus to the power n. Actually, this is imprecise. This is imprecise. This is going to go like lambda plus to the power n, right? So in other words, in the limit for n going to infinity, what matrix is the largest eigenvalue of the transfer matrix? And now, if I go back to what I had, well, the largest z, therefore, in the limit for n going to infinity, the largest eigenvalue was ebj plus e to the minus bj, which is equal to 2 cosine hyperbolic bj. So I will get 2 to the n cosine hyperbolic of bj to the power n. But if n goes to infinity, n minus 1 and n are the same, right? If n is much, much larger than 1, you can forget about this minus 1. And therefore, in the thermodynamic limit, the two partition functions are identical, and they're also the free energies are going to be identical, and everything else. Okay? Now, in general, you can use this. How's it called? Transfer matrix to solve the problem not only with h equals 0, but also with finite h. And in particular, one thing that you can do is compute the free energy for finite h. And I leave it to you as an exercise to actually compute the free energy at finite h, so as a function of beta h and beta j, and then compute using the free energy the magnetization, which is equal to minus df dh, and study the limits of beta going to 0, beta going to infinity, etc., etc. I mean, all the usual things we have done up to now. Okay? Now, the transfer matrix is a very general method. Now, here we have been using it. Yes?
Why don't we calculate like entropy or?
Well,
Yeah.
you can, you know, actually, yeah, since you say it, also compute the entropy and the energy and whatever, you know, all the quantities that you already calculated. The reason I asked you to do the calculation for the magnetization is that this is a calculation that you cannot do by the recursion method, right? All the other calculations we have already done with the recursion method, but the calculation of the magnetization, you cannot do it with the recursion method, simply because with the recursion method, you cannot put in a magnetic field. And therefore, life is more complicated. Okay, so now, some generalities about the transfer matrix method. Now, the transfer matrix method, let me summarize it here. So we have been using it for the one-dimensional Ising model. We wrote the partition function with periodic boundary conditions in this direction. Periodic boundary conditions, PBC. We wrote the partition function Z as trace of V to the power n, where V is essentially the matrix, the transfer matrix that connects the configurations of neighboring sites. And since each neighboring site has a phase space that consists of two possibilities, up or down, The transfer matrix is the dimension of the transfer matrix is 2 by 2, right? And nothing else. Now, if I would solve the same problem, let's say, instead of solving an easy model, I would solve a POTS model. Now, the transfer matrix is going to be a matrix that connects configurations of neighboring sites, but the local phase space of one of these sites now has not dimension 2, but has dimension q. So I will still be able to write the transfer matrix, sorry, the partition function as v equal to trace of v to the power n, but the dimension of my matrix V now is going to be Q by Q. Okay?
Yes, yes.
Excellent. And by the way, you could try to, actually, probably we will do it later on. Yes, actually, we're going to do this exercise later on for the POTS model. So let's leave it. This is going to be solved. So next time, but if you want to try to practice a bit before next lecture, try to solve the POTS model using the transfer matrix method. And you will see that it's not that straightforward to solve it analytically, simply because while before I had to diagonalize a 2 by 2 matrix, now I have to diagonalize a Q by Q matrix. And Q by Q, if Q is sufficiently large, is not that simple. Suppose now that instead of having a one-dimensional model, I have a two-dimensional model, like this one, defined on a square lattice. So what I have is a model in which I have, let's say, an easy model, in which I have n columns and m rows. Now, as before, so let me do it like this. Before, the transfer matrix was connecting the configurations of different points in phase space. Now, in this case, the transfer matrix is going to be an object that connects configurations. Nah, too bad. Well, that connects configurations of different rows, or different columns in this two-dimensional lattice. Okay? So you will still be able, also in this case, to write Z equal to trace of a certain transfer matrix to the power n. But the main difference is going to be what is the dimension of the transfer matrix. Now, the dimension of the transfer matrix is going to be the dimension, this time, of the phase space of one column. And the phase space of one column has dimension 2 to the power m. So the transfer matrix is going to be a 2 to the m times 2 to the m matrix. It's going to be a huge matrix, in other words, when you go to 2 dimensions. And in 3 dimensions, it's going to be even more complicated, because you're going to have, instead of having columns, you're going to have planes, and so on and so forth.
Sorry,
So, yes,
I have a question.
yes.
So About the dimension, it's 2 to the power of m because you have two possibility of spin with m points.
Yes, exactly.
Okay. And do they interact between the columns? I mean, they interact between the columns, right? You say
Of
that.
course, they interact
And then
here and
you.
they interact here.
Oh, how about the inside of the columns? Do
Yeah, they interact also there. Yes, yes.
I mean,
absolutely.
you with the logic of the transfer matrix just now, you handled the case for one-dimensional. So I think that you make this column to pretend that it's a one-dimensional system, and then so my question is like how does it exactly being handled inside the column, like.
How do you handle the summation of all the indices within the same column?
Yes.
Yeah, well, that's not a complicated because I always have to sum over all the indices, right? So what I'm trying to say is the following. So suppose that you fix one configuration of this column and one configuration of this other column. Now the transfer matrix is a function, is going to be a function in this case of the configuration of column 1 and the configuration of column 2. Now once I fix the configuration, it's trivial to compute what is the energy actually, taking into account also these interactions. But now I have to sum over all configurations. And the point is that when I sum over all configurations, then V is seen as a matrix that has as indices the configurations of the columns. You see what I mean?
Oh, sorry, come again, the last one. What?
Look, I mean, the matrix V, the transfer matrix in this case, is going to be a matrix that has as indices the configurations of the columns. Okay?
Yes.
Now, we should do all the calculation in detail, but then you see that once I fix the configuration, sigma 2, it's not hard to write down the energy of the column itself. In other words, V, in this case, is going to have two contributions, e to the h column with sigma 1. Okay? This is the Hamiltonian of this column with all the interactions evaluated on the configuration sigma 1. Then you're going to have the Hamiltonian on the second column evaluated on the configuration sigma 2. And that also you know how to compute because you know what is the configuration. And then you're going to have the Hamiltonian V connecting of all these bonds, connecting the two columns. That is going to depend, or let's call it W, on sigma 1 and sigma 2. So this is going to be the generalization to this particular case of what I had before. You see, before, let's look at what we had before.
Sorry?
Yeah, just a second. Let me finish here and then I'll let you ask the question. You see, in this case, my transfer matrix is for the one-dimensional case, the energy of on the configuration of sigma plus the energy on the configuration of sigma prime. If I have sigma and sigma prime that are isolated, that they have essentially just a magnetic field, plus beta j plus the interaction term, which I call W sigma sigma prime. So you see how the structure will generalize to this case, right? Actually, here you should put a factor of 2. Okay? You see the point? How everything will generalize to the 2-dimensional case. But look, the point I wanted to make is not this generalization, which is beyond the scope of this course. So of course, I will never give you 2-dimensional problems to solve. What I wanted to explain is that there is a conservation of difficulty in life and in physics. So it's not that now I introduce to the transfer matrix and all problems in statistical mechanics becomes simple and solvable. Because the problem of of computing the partition function, let's say in 2 dimensions or in 1 dimensions, is transferred to the problems of diagonalizing a matrix. So it's rewritten in a different way. And diagonalizing a big matrix, a 2 to the m times 2 to the m matrix, is not a simple task. It can be done numerically. There are good algorithms to compute the largest eigenvalue, but it's not something that you can do like this. So the transfer matrix is not the solution to all problems. It's just a rewriting of the problem in a different form. Please, what was the other question?
Yes. What if we choose the interaction between the lines in place of columns? We get the same result.
Yeah, you get the same result, but the matrix, so Z is going to be trace of V to the power M.
Yes.
And the dimension of the matrix is going to be 2 to the n times 2 to the n.
Yes.
So
okay.
Everything is going to be the same. Any other question?
Yes, Professor.
Yes?
Yes. I have a question.
Yes, please ask the question.
When you introduce transfer matrix,
I cannot hear you well.
when you introduce transfer matrix, then
It's still incomprehensible. Maybe you want to write it in the chat.
okay.
Okay, I'll be waiting for it to appear in the chat.
Pooja, please mute your mic if you don't use it. Thank you.
Okay, so did you write it? No.
Yes, Professor, I'm writing.
Now I can hear you actually. So try again to ask the question.
When you introduce transfer matrix, then you used periodic boundary condition. Then
Yes.
can I be clear that for introducing transfer matrix, we always use a periodic boundary condition?
Well, it's not necessary. You can introduce the transfer matrix also without periodic boundary conditions. The problem is that if you don't have periodic boundary conditions, instead of having trace of V to the power n, what you're going to have is that your partition function is V to the power n, that remains, but it's not a trace, is the matrix element of v to the power n in between two vectors that represent the boundary conditions that you put on the first and the last side or column, depending on what you're doing. Okay? So you can also do it without periodic boundary conditions, but it becomes more complicated. With periodic boundary conditions is actually the simplest possibility, because instead of taking a matrix element, you have a trace. And then for the trace, it's much simpler to compute it by diagonalizing the Hamiltonian. You don't need to know what are the eigenvectors. You just need to know what is the largest eigenvalue to compute the trace in the thermodynamic limit. All right. Are there other questions?
And also,
Yes.
the dimension of B for Ising model is 2
The
cross
dimension of V
yes,
for Ising model, yes.
2 cross 2, and for pot model is Q cross Q, and I think that it is the ground state degenerate state for both, and
I didn't get it.
the ground
You think
state yes, ground state degenerate state for both in case of Ising model 2 cross 2, and in case of pot model Q cross Q.
yes?
Yes, it is a. Can I write here the dimension of Isaac model as a 2 cross 2 is a can I understand here 2 cross 2 is the ground state degenerate state, and the Q cross Q is just the ground state degenerate state of pot model.
Is the what? Is the ground?
I think the ground state, she said.
Ground state
No,
degenerate.
no, it doesn't. I mean, it's not. I didn't discuss ground state. Q is the dimension of the local phase space. What does it mean? If I take just one site in my lattice, and if I look at the variable that is defined on that site, sigma, I have to look at how many possible values can take this variable. For the easy model is 2 possibilities, +1 or -1. For the POTS model is actually Q possibilities, between 1 and Q. So this is the difference. Then of course it is true that as a consequence of this, the POTS model has Q degenerate ground states at t = 0, of course, and the easy model has only 2 degenerate ground states. But this is just a consequence of the dimension of the local phase space. Okay, so is it clear now?
Yes, Professor.
Okay, great. So, well, we don't have much time, so I'll just mention one thing without proving it. There is actually something called a quantum to classical correspondence, which comes from the following fact. Sometimes, so it is actually convenient sometimes to write your transfer matrix in the following way: e to the minus a times h. This comes through, I mean, why it is useful to do this comes from the fact that, for example, Z, I told you is essentially equal to, for non-periodic boundary conditions is equal to this. And this looks like, if I rewrite V in this way, you see this looks like 1 e to the minus n times a times h, which up to a rotation to imaginary time is like a propagation in quantum mechanics. Okay, so this is why sometimes people like to write the transfer matrix as e to the minus a times h, because it looks like quantum mechanics, like a propagator or a time evolution in quantum mechanics. Now, this gives you the possibility to introduce what is known as the quantum to classical correspondence. The idea is essentially the following. Think about the easy model. In the easy model, we were starting with a classical model in one dimension. We wrote the partition function z as trace of v to the power n. Now, if we rewrite the transfer matrix V as e to the minus a times h is going to be a 2 by 2 matrix. And the 2 by 2 matrix is going to be a 2 by 2 symmetric matrix. And a 2 by 2 symmetric matrix in quantum mechanics describes the physics of just one single quantum mechanical spin. All right? So in a sense, when you use this writing, what you do is end the concept of transfer matrix. You reduce the problem of solving a one-dimensional problem in classical statistical mechanics to diagonalizing a quantum mechanical Hamiltonian in d minus 1 dimensions. So here d was equal to 1. Sorry. Was equal to 1. And of course, here I have the Hamiltonian of a single spin. So d is equal to 0. It's a zero-dimensional system, a single spin. It doesn't have any dimension. Now, this is a very important.
Sorry?
This is a very important. Yes.
How is it d is equal to 0? Because we have up and down.
No. D is the space dimensionality.
Oh, okay.
So if you have just one object, it doesn't, it's localized. So it's like formally it's a zero-dimensional object.
Yeah.
Now, why this idea is interesting and important? Because if you take it in 2 dimensions, so you take a 2-dimensional easy model on the square lattice, then you have that V equal to e to the minus a times h, right? So for the 2-dimensional case, where h now is not a 2 by 2 matrix, but is actually a 2 to the m times 2 to the m matrix, according to what I told you before. Now, a 2 to the m times 2 to the m matrix in quantum mechanics is an Hamiltonian that describes actually a one-dimensional spin system, right? If I have spins in one dimension and I have one m of them, the Hamiltonian is going to be 2 to the m times 2 to the m. Okay, this is in quantum mechanics. So therefore, in this case, I pass from a d equal 2-dimensional classical problem to a d equal 1-dimensional quantum problem. And in particular, the easy model here is minus j sum over I and j nearest neighbors, sigma I, sigma j. The Hamiltonian h, in this case, the quantum mechanical Hamiltonian can be shown to be equal to minus, let's call it j tilde, sum over I, sigma z I, sigma z I plus 1, plus lambda sum over I, sigma x I. So if I write the transfer matrix in this exponential form, what stays in the exponent, this quantum mechanical Hamiltonian that stays in the exponent, is still an easy model in one dimension, but with a transverse field that makes the spins, individual spins, rotate. Anyway, this idea that you can go from classical statistical mechanics to quantum mechanical problems using the transfer matrix is a very general idea that is being used a lot in the literature and has a name, is called quantum to classical correspondence. In other words, it tells you if you're able to solve a quantum mechanical problem and compute the eigenvalues of a quantum mechanical problem, then you're able to compute the transfer matrix, then you're able to compute the partition function of the classical problem, and vice versa. It's an interesting idea. We are not going to use it much, it's a bit too advanced, but I thought that you would find it interesting that there is this correspondence between quantum mechanics and statistical mechanics at the level of transfer matrices. So I invite you to think about it a bit more. Next time we're going to talk again about transfer matrices. So if you have questions about this quantum to classical correspondence that might look weird to you, please ask on Wednesday next time. Yes.
Where can I read this quantum to classical correspondence?
When you can use it?
Read. I mean, you said to think. I mean, yeah. So I want to read it.
Well, it's not something. Look, I mean, I'm going in a bit advanced territory here, right? So it's not something that you find in elementary statistical mechanics books. So I'll tell you the name of a book, but you will find it a bit complicated. Let's put it this way. There is a book by Giuseppe Mussardo. It's called Statistical Field Theory. So even the title is scary, right? Statistical Field Theory. Is edited by Oxford. Or you can read about it in the first chapter of the book by Sachdev, which is called a dynamical. Sorry, no, it's called not dynamical. Quantum phase transitions. And is edited by Cambridge. All right, so go through, I mean, but again, just think about what I just said. I mean, don't go too much into the details of this because it's complicated territory. I mean, it's not easy. Let me put it this way. There are loads of details. All right, so, okay, so are there other questions? Okay, so if not, let's meet next Wednesday, usual time. Okay?
Okay.
Okay.
Thank you.
Bye-bye, guys.
Bye-bye.
Okay, thank you.
Bye.
Goodbye.
Bye.